unanimity games, and Harsanyi dividends. These are the topics of today's lecture. Unanimity games. A unanimity game is a special kind of a game. N is the grand coalition and omega S is called the unanimity function. It's a special kind of a value function which is defined in the following manner. First of all, we need to define omega S in terms of S, which is some subset of N. The unanimity function omega S of any coalition C is equal to 1 when S is contained in C, when S is a subset of C. This is depicted here. Omega SC equals 1 because S here is contained in C. S is a subset of C. Otherwise, when S is not a subset of C, that is when S is not contained in C, then omega SC equals 0. This is depicted here. S is not fully contained in this C here. Therefore, omega SC equals 0. The unanimity basis is the set of all unanimity functions omega S. And since we can define 2 to the n minus 1 number of subsets S, therefore the cardinality of the unanimity basis is 2 to the n minus 1. Here's an example. Let's take n equals a comma b, so we have a grand coalition of only 2 agents, and therefore we have 3 possible unanimity functions, omega a, omega b, and omega ab. So these are the mappings. So omega a for each coalition C, these are the values of omega a, these are the values of omega b, and these are the values of omega c. Why is this? When C equals A is contained in C, so this is 1, but A is not contained in B, so this is 0, and A is contained in this coalition here, AB, this is A, so it's a 1 here. Likewise, omega B for AB and AB are 0, 1, 1, and omega AB is 0, 0, 1. So each of these mappings, omega A, omega B, and omega C, is a basis function, and together they form the unanimity basis. So the unanimity basis of this little coalition here, or rather this grand coalition, is omega A, omega B, and omega AB. Next, I'll demonstrate with the simple example that the value of a coalition can be expressed uniquely as a linear combination of the omega s's. That's why the omega s's are called the basis vectors or basis functions, and B, the set of all unanimity functions, is the unanimity basis. So this is my claim for our little example. V of C is delta V comma A of omega AC plus delta V comma B omega BC plus delta VAB omega ABC. So I have some value function here, V of C. For A, B, and AB, these are the specific values. And this is my claim that I'll ignore the V's here. I'll just call this delta A, delta B, and delta AB for simplicity. And so these deltas are the coefficients, and each value here can be uniquely represented as a summation of the deltas and the omegas. Let's see how. Now we consider the coalition of A alone. So the omegas are omega A equals 1, omega B equals 0, omega AB equals 0. So plugging in these values, omega equals 1, omega B and omega AB are zeros, whence VC, which is equal to 7, is simply delta A. So delta A equals 7. Likewise, when C is equal to B, this is 0, delta A is 0, delta B is 1, and delta delta AB is 0, whence I only have this term here, and the value is equal to 8, whence delta B equals 8. And in a similar manner, delta A plus delta B plus delta AB equals 20. Because all threes are 1, so I included all three deltas here, and that's equal to the value of the coefficient 20. Whence V of C is equal to 7 times omega AC plus 8 times omega BC plus 5 times omega AB of C. So this illustrates how we can represent any value uniquely in terms of the unanimity functions. So this is what we just saw, and we can extend it further. So this is the unanimity basis. It's the set of all unanimity functions, and the value of any coalition, not necessarily of size 2, but any coalition, can be uniquely expressed in terms of the unanimity basis. V of C equals summation over all subsets of the grand coalition of delta S times omega SC. Harsanyi dividends. So this is my claim here, and I just demonstrated this earlier for a simple game with two agents A, B, and this is my claim here, and these deltas are called the Harsanyi dividends. So here's my formal claim theorem. The value function, any value function, can be uniquely expressed in terms of the unanimity functions in the basis with Harsanyi dividends, that is the deltas, as the coefficients. So given any coalition C, the value of C is equal to summation over all subsets of the grand coalition of delta S times omega SC. Proof. Now, how many possible subsets or coalitions can we define? 2 to the n minus 1. And so let's index them, C1, C2 until C, 2 to the n minus 1. These are all the possible coalitions, and so we have their values V of C1, V of C2 until V of C sub 2 to the n minus 1. And on the right hand side, each of them, according to this claim, is equal to this. Delta V of S, omega S, C of 1 here, this is for C1. And likewise for C2, this is summation of delta S, omega S of C2. Now we have 2 to the n minus 1 values. And here each term in a summation also has 2 to the n minus 1 possible total number of terms, not possible, sorry. The total number of terms in each summation is also 2 to the n minus 1. So we have 2 to the n minus 1 possible deltas, variables, deltas, and that many number of equations. Since the number of variables is equal to the number of equations, here linear expressions, therefore we can obtain unique solutions for the deltas, whence each V of C is uniquely expressed as the summation over all S's delta S WSC. Now let's take up a bigger example and we'll try to compute the Harsanyi dividends specifically for this game here. The values are defined here and these are all the unanimity functions, omega A, omega B until omega ABC. So what I'll do first is I'll form a matrix out of all these zeros and ones. Now, caveat here, it might be a little confusing, but here I have S's which are subsets of the grand coalition, A, B, C until ABC, which is the grand coalition itself. And here I have, again, A, B until ABC. Now, think of it this way. Each of these is a coalition of the or a sub-coalition of the grand coalition. And each of these S's is merely a subset of the grand coalition. Think of it that way. And so each of these rows is a basis, or a basis function rather, of the basis set or unanimity basis set. Omega A, S is A now. Omega A of each coalition is given by these values. Omega, where S equals B of the coalitions are given by these values, and so on. So next, as I said, I'll form a matrix out of all these zeros and ones. So this is my matrix. I'll call this uppercase omega, bold omega. It's a matrix. And each row is a unanimity function. So each row of this matrix is a basis vector. And also note that the diagonal elements of omega are all ones. Hence, you know that the eigen values would be, the product of the eigenvalues would be equal to 1 because this is an upper triangular matrix. Whence we can see that omega is non-singular. In other words, the inverse of omega exists. And next what I'll do is I'll form a vector out of the values. So this is my omega and this is my vector v. It's by default all vectors are column vectors. Whence I have this relationship here. These v's equals this matrix omega transpose. Don't ignore this little transpose here. This is omega transpose and this is my vector of deltas, the Harsanyi dividends. Solving for delta, I get these values for each delta. Now in PowerPoint it's impossible to differentiate between bold deltas and italic deltas, so it might be a little confusing, but anyways, so these are the different scalar deltas that I obtained, and plugging them here in this expression I get v of c equals this. So 1, so this is 1 and this 2 corresponds to this 2 corresponds to this 2, and so on. I've color coded them for clarity. For example, v of AC is equal to omega AC. Now B is not contained in AC, so omega BC equals 0. I will just ignore this. C is contained in this coalition AC, so I've included this here. This is omega C would be a 1, and then AB is not contained in AC, so again I'll drop this term because omega AC is 0, and then here AC and this C is AC2, so this omega is 1, whence I have 4 here, and this 2 again, BC is not contained in AC, so I'll drop this term here, and omega ABC is uh, not contained in uh, AC, so I'll drop this third term here, whence this is what I get. And this 7 here is actually the value of the correlation AC that I had defined earlier. So we have this linear relationship V equals omega transpose lambda. And since omega, this matrix omega is non-singular, we can solve for delta. Delta is the inverse of omega transpose times V. And we can obtain delta. Delta will be a unique solution. So this confirms our previous theorem which we proved. How to compute the Harsanyi dividends? We shall see two ways to compute the Harsanyi dividends. One is this recursive expression here, delta S equals V of n when S is of cardinality 1, and for higher cardinalities, delta S is equal to V of S minus summation over all proper subsets of S times of delta T. And this is a non-recursive expression to obtain the same Harsanyi dividends. Delta S is equal to summation over all subsets T of S, -1 to the difference in sizes between S and T times value of T. Before we prove the theorems, actually I'll only prove the first theorem. The second one will be left as an exercise. Let's take up the previous example and compute the Harsanyi dividends using these two expressions first. Now, before we do that, here's one thing you should note. In the recursive expression, I'm considering in this summation here proper subsets of S only, not S itself. Here, in the non-recursive expression, this summation is over all subsets, which includes S. Now, let's take up our example. We already know that these are the values of the Harsanyi dividends that we computed directly. So we'll keep these deltas that we have pre-computed earlier here, and then we'll try to apply the recursive expression first. Let's consider when S has a cardinality of 1. So what are the possible S's? A, B, and C. So in this case, delta S is equal to Vs itself. So delta A equals value of 1, which is value of A, excuse me, which is 1. Value of B is 2. So delta B is 2, and likewise delta C is 2. And these can be verified from our earlier computation. Now let's proceed to S's of cardinality 2. So we'll have to apply this expression here. So let's consider S equals A comma B. So delta AB is equal to value of AB minus summation over all proper subsets of S delta T. What are the proper subsets of AB, A, and B? So we have negative delta A, negative delta B. And plugging in the values, we get VAB equals 5 minus delta A equals 1 and delta B equals 2. So 5 minus 1 minus 2 equals 2, which verifies this here. And likewise, delta AC is equal to value of AC minus what are the subsets of AC, A and C, and plugging in the numerical values, we get 4. And for delta BC, we again get 2 here. So this verifies the deltas of all subsets S of cardinality 2. Now let's take up ABC. This is S here, ABC, and so V of S, we'll apply this expression here, delta of ABC equals V of ABC minus summation over all proper subsets of their deltas. So what are the proper subsets of S? S is ABC. So its proper subsets are AB, AC, and BC. These are of cardinality 2, and we have its proper subsets A, B, and C of cardinality 1. And so plugging in the numerical values, we get VABC is 10 and negative delta AB. Delta AB is 2. Delta AC is 4, delta BC is 2, and we have the values of delta A, delta B, and delta C here. So we get negative 3. This is negative 3. So we have verified that the recursive expression works. Next, we look at the non-recursive expression. So next, consider the non-recursive expression. First, we'll take up the case where S has a cardinality of 1. So S can be A or B or C. And when S equals A, it has only itself as its subset. And so the T can only be equal to S. So this S minus T, the size difference is 0. Negative 1 to the 0 is 1, and value of the subset A is 1. So this delta A is 1. Likewise, delta B is 2 and delta C is 2. Next, let's take up the case where S has a cardinality of 2. So here's S, this is S, and what are its subsets? T, AB, A, and B. So these are the different possible T's. So when T equals S, we have negative 1 to this, their size difference is 0 of V of T, which is V of S itself. So delta AB equals, this is my first term, VAB. And then when T equals A and S is still AB, so the size difference is 1. Negative 1 to the power of 1 is 1, whence I have this negative sign here. And what's V of T in this case? V of A. And likewise, this is negative V of B is the third term that I get here, and plugging in the numerical values, I get 2. And in a similar manner, I can work out delta AC and delta BC to obtain 4 and 2 respectively. So I have verified all these deltas again. Now let's look at this ABC. So this is my S. And what are the possible subsets? ABC itself, AB, AC, BC, then A, B, and C. So these three, well, first of all, ABC is a subset. So when t equals ABC, I have -1 to the 0 of v of t, which is s, so value of ABC. Then here are the three terms of when t is of cardinality 2. So t is size of t is 2, size of s is still 3. So 3 minus 2 is 1. -1 to the power of 1 is negative. So I have a negative sign in these three cases, and then value of the coalition. So value of AB, value of BC, and value of AC. Excuse me, I have value of AC and then value of BC. Next three terms correspond to when t equals A, B, C. In all three cases, their sizes are 1. So 3 minus 1 is 1 here. So this -1 squared is 1. Whence I have plus, plus, and plus signs here. And then the values of t is A, B, and C. So value of A plus value of B plus value of C. Plugging in the numerical values, I get -3, which verifies this last delta here. And so the non-recursive expression to compute the Harsanyi dividends also was verified. Let's formally try to prove this recursive expression. First, we'll consider the case when S has a cardinality of 1. So omega S of S is equal to 1 because S is contained in S itself. So omega SS equals 1, obviously. And since S has a cardinality of 1, it has only one element in it, only one agent in it. So for any t that's not equal to S, omega t of S must be equal to 0. So next I'll use this expression. What I've done is I've replaced C with S, and so this C is an S here, and these S's I've replaced with T's here. So the summation is carried out over all T's. And so what happens to all the terms in this summation? There's only one term, omega SS, which is equal to 1. And all the other terms for which t is not equal to s become equal to 0. This is 0. So there's only one term in this summation for which omega is equal to 1, and that's when t equals s itself. And so this is equal to 1 in that case. So we have v of s equals delta s omega ss, which is equal to delta of s. So v of s equals, delta of s equals v of s. So for cardinality 1, we have verified this expression. Next, we'll consider s's with cardinalities above 1. So omega t of s is equal to 1 when t is contained in S, and that is when either t is S or t is a proper subset of S. So these are the two cases where omega t of S is equal to 1. We are looking at this here. Omega t of S is equal to 1 when t is contained in S. And this t equals S, I don't have a third picture here, but that's when t and S overlap, t equals S. So anyways, omega t of S is equal to 1 in these cases, and for this case, omega t of S is 0. For all other cases, omega t of S is 0. And as before, I'll use this expression for the value of S. V of S is summation over all possible subsets T, delta T, omega T, S. So this is what I have. Now this summation, I'll divide it into three different parts. First part is when T equals S, so that's delta S omega SS, And the second part is where T is a proper subset of S. So this second part is a summation over all T's which are proper subsets of S of delta T omega T S. And the third part is when T is not a subset of S of this same delta omega. Now this subsumes all other cases except when T equals S and T is a proper subset of S. So now let's exploit these values here. Omega SS, when T equals S, we know that this is equal to 1. And when T is a proper subset of S, again, we know that omega T of S equals 1. But when T is not a subset of S, in that case, omega T of S equals 0. So this third term contains all zeros here. Omega T of S is always zeros, and here it's 1 and here it's 1. So we have V of S equals, so this first term here is delta V of S plus summation over all subsets, proper subsets T of S of delta Vt. This omega Ts is equal to 1, so we just drop it. Whence we get V of S equals this expression here, or delta S equals V of S minus summation T delta T. And if we compare it with the statement of the theorem, when S has higher cardinality, then we apply this expression here, which is the same as what we arrived earlier. I'll leave the non-recursive expression as an exercise for everyone. This is what we shall look at in future. You can try this yourself too. The Shapley value of the unanimity game is equal to, so for every agent I that's contained in S, that belongs to S, the Shapley value is 1 over cardinality of S. And the Shapley value of an agent that's not a member of S is 0. And this can be proved. You can work it out as an example, although I'll prove it in a subsequent video. And using the previous theorem, you can prove that given any value function, V, the Shapley value can be expressed in this manner: summation over all subset S which contain I of delta S divided by cardinality of S.